This is Introductory Nuclear Physics course, and it is for both undergraduates and graduate students. Today's talk is about the fusion reactions, how fusion reactions can be controlled. It's a three-part series, and today we will talk about the first part. I am Dr. Nasir Mirza. We will be discussing fusion reactions today. Very rightly, we can say that the fusion is going to be future energy source. It is a reaction in which two lighter nuclei get fused together to form a large nucleus. And when this happens, energy is released. The binding energy curve shows this. You can see here with the very small values of A, the number of nucleons A shown on x-axis, and y-axis has the average binding energy per nucleon in million electron volts. The hydrogen isotopes, helium, the lithium, the helium-4, the lithium, the beryllium, boron, carbon, nitrogen, and then the other isotopes, and we reach here at the peak. It is iron, which is most tightly bound nucleus, and it has very high average binding energy per nucleons. Then again, the curve shows a decrease for very high A numbers, and things like the lead, the uranium are at the tail, and they have lower binding energies as compared to the iron and isotopes here. Similarly, the binding energies for these isotopes are very low as compared to the iron. Therefore, these are going to fuse to gain the higher binding energy and more stability. This is the reaction in which the protons or the hydrogen nucleus gain energy, and then they form the helium, and the helium is relatively higher binding energy value. And that's how the sun is getting its power and energy, and much higher energy content is coming from the fusion of these isotopes. The combinations with the heavy waters element, the deuterium, the tritium, the helium-3, all have the low binding energies and can produce high binding energy elements when they combine together. We have seen that the natural fusion is occurring in stars. The stars have the hydrogen atoms, and the nucleus of hydrogen is proton, and they get converted into helium. 4 protons combine to form helium, and the 2 positrons and 2 neutrinos, and the conversion is about 0.7% of the initial mass to the energy, and that's a very large energy which is emitted in the fusion reaction. 10% of the sun's initial hydrogen content can power about 100 billion years need of sun's needs. So the natural fusion available in stars is the form of the source which keeps the stars shining and the sun emitting the energies. Here we show a binding energy curve in a very different manner again, and here the binding energy per nucleons is shown as a function of the number of nucleons in the nucleus, and in a different manner. And we see here the manner is that 0 is at the top, and the average energy is increasing in this downward trend. So highest stability is with the iron, and the lowest are these isotopes. Similarly, these isotopes of uranium are comparatively unstable. They would like to become stable by fission. If we look at the thermonuclear fusion reaction in the sun has very high temperature. It's about 16 million degrees Celsius in the center. At such high temperatures, atoms change into ions and electrons. The state is called plasma state, and it is enough energy that these protons will fuse together despite their mutual repulsion due to the Coulomb force, and then can convert them into deuterium and then eventually to the helium. Reaction per mole is about 20 million times more energetic than chemical reactions that take place in journal. So 4 proton mass becomes an helium nucleus, and its mass is a little bit smaller as compared to the 4 proton individual masses. And the 2 neutrinos and the photons are emitted. And this mass change is really the reason for the emission of the energy in the fusion reaction. Let's talk about the plasma. The fusion reactions can only happen at very high temperatures, about 100 million degrees centigrade. At these temperatures, matter exists in a state which is called plasma state, where ions and electrons are separated and coexist. So in plasma, electrons are stripped from the nucleus, and they can be independently moving as a gas. Plasma consists of charged particles, the ions, the electrons, and they can coexist. Plasma has positively charged nuclei, and they repel each other, so normally fusion does not happen. Ions must have the kinetic energy high enough to approach to close enough for the attractive nuclear force to act on them and to bind them and to overcome the electrostatic repulsion. The Coulomb barrier, which is crossed once, will allow the nucleus then to fuse together and form a bigger nucleus. In doing so, the energy will be released as a mass effect, and this energy will be large enough to produce or do other things. So we can safely say that the plasma is an ionized gas. It is the 4th state of matter, the solid, the liquid, the gas, and then the plasma state. Mixture of positive ions and negative electrons with overall charge neutrality is in the plasma. Plasma can shield itself from the external fields and can have the charge neutrality still present. Plasma constitutes the 4th state, and it is obtainable at the temperatures exceeding 100,000 of degrees Kelvin. Plasma conducts electricity. It can get heated and can be confined by the gravity, or can be confined by the magnetic fields, and can be confined by the inertia. The stellar all masses have this state plasma with them, and the plasma becomes visible when the visible light the spectrum is emitted as the charged particles are accelerated or deaccelerated. There are several problems with the controlling plasma so as to sustain diffusion reactions. Plasma do pose a problem. We must confine plasma at 100 to 50 million degrees. 100 million degrees for DD reaction, and for other reactions we will show. All with the good fuel flow, heat extraction, tritium supply, and many other things done simultaneously. The problems are that the plasma dynamics dictates the plasma instability, and it will eventually hit something and will collapse. There are turbulence in the plasma, and plasma confinement is a difficult thing. It is being still pursued, but with the ambition that ultimately a energy source will be available to the world, which will be very clean and very cheap. Ions must be held together long enough to fuse for the fusion to occur. So plasma controlling, not only controlling is needed, that is, it should be dynamically stable, but we must put it together for a long time so that the fusion occurs. No wall material can contain a plasma that is millions of degrees hot. Either plasma will damage the wall, or will cool the plasma, and its temperature reduction will immediately cause the plasma to become a neutral gas. Fusion is a natural process in the sun. Fusion with the two protons to make a bigger nucleus is difficult on Earth, but it is easy on stars and sun. Because two protons repel each other, they have the Coulomb electrostatic force. So if you want to reduce the R, the distance between the two nucleons, the 1/R behavior dictates that the potential will go high, and it will be a repulsive potential, a positive repulsive potential. It becomes very high, but beyond certain limit, this becomes a negative attractive potential, and this is the position after which the strong nuclear force becomes very dominating force, and therefore it is the attractive part which is available. However, to surpass this, we need high energy, and high energy is classically available through temperatures. So about 10 to the power 10 Kelvin are needed sometimes to overcome this barrier. Temperatures mean the average kinetic energy of the particle. Remember, average kinetic energy of the particle is 3 kT, 3 divided by 2, and 3 stands for the three-dimensional particle behavior, and K is Boltzmann's constant, and T is the temperature. Sun will manage to do this at 10 to the power 7 Kelvin because of the quantum tunneling that the particle will penetrate through and will become part of this attractive potential. Still, it is very improbable reaction, and the reason is that the PP chain is a slow chain, and therefore the sun, with the immense gravitational pull, can produce high temperatures that are needed to do this. If we look at the proton fusion cycle, the fusion of the two protons into deuterium is given by this reaction, which emits 0.042 million electron volts, and the deuterium is formed. The deuterium nucleus, this is a slow process, and the beta plus decay of the deuterium to deuterium is extremely rare, and therefore vast majority of the time this decays back to the hydrogen. But positron, when is emitted, it immediately annihilates with the electron, and therefore it is lost. And two gamma rays are produced, and these two gamma rays with the energy 1.02 million electron volts. After this, the deuterium produced in the first stage can fuse further to produce the lighter isotope of the helium, and helium-3 is produced. So proton-proton fusion cycle is slow because of this reaction, and eventually it gets the helium, and the large amount of energy is emitted. The total energy emission is high. So formation of high A number materials continue to happen in stars and in sun because of the fusion reactions, and the helium-3 reaction is where helium-3 and helium-3 combines to produce helium-4 and two hydrogen nucleus, that is a proton. So helium-3 and helium-4 combines to produce beryllium, lithium-7, and helium-4. The heavier elements are produced. Remember the binding energy curve, it states that these are much stable because they have the high binding energy per nucleon as compared to the original helium. And eventually these are going to be stable. However, if the beryllium-7 with the proton is absorbed, then boron-8 and beryllium-8 are produced, and this can continue to produce even higher elements. Now we look into the possible fusion reactions on Earth and the fusion reactions that are employing the deuterium and tritium, that are the isotopes of the hydrogen, are shown here, where the D and D is basically the hydrogen isotope. They are combining together to form helium-3 and the neutron. They can also have the 50% probability of producing tritium and a proton. Proton is a charged particle and the neutron is a neutral, and therefore the majority of the energy which is carried out by the neutron is high, and the proton is also high. However, the proton can be stopped easily, and neutron is difficult to stop. The DT reactions are where the helium-4 is produced and a neutron, and deuterium and helium-3 produces helium-4 and a proton. However, these reactions are with the higher energy that the neutrons are carrying 14 million electron volts, and 3.5 are with the helium. So 17, more than 17 million electron volts are produced in this fusion reaction. They are producing more energies. The easiest and more energetic nuclear reactions are due to the deuterons and the tritium nucleus. They are producing also alpha particle and the nucleus of the helium and the neutron. So energy released in DT reaction is about 17.6, and 1 kg of this fuel will be providing the requirement of 1 gigawatt power station for a day, for a whole day. Day means 24 hours with 60 minutes per hour and 60 seconds per minute. If we look at the fusion reactions cross-sections, we see very high cross-sections at certain energies, and the cross-sections going up as the energy is allowed to increase. So deuterons energy increase results in the D reaction or DT reaction with a high probability. If the kinetic energy of the deuteron is between 10 and 100 keV, the reaction probability becomes high. Let us look at the advantages of the fusion process. There is a huge supply of fuel, that is a deuterium available in seawater. It is relatively safe and clean, no radioactive waste. there is possibility of direct conversion. That is, the charges and the neutrons are there, therefore energy can be directly converted, and so it's a high efficiency system that can be built. But the problem with the fusion process is we need very high temperatures. We need to create force against the force of repulsion for positive charges. And plasma cannot be easily confined in a vessel because of its dynamic instabilities. Let's find out the energy released in a typical fusion reaction. Let us consider D and T, and helium-4 is produced, and a neutron is produced, and the Q value of reaction is released. Let's find the mass difference. Mass of the deuterium, mass of the tritium, mass of the helium, mass of the neutron, with the charges are written, and it is being told with the help of the mass of the hydrogen. So the total mass deficit is basically the mass before the reaction and the mass after the reaction. It is equal to 0.0187 times the mass of hydrogen, and mass of hydrogen is 1.67 into 10 to the power minus 27 kg. So for this mass deficit, the energy from the Einstein's formula is E is equal to delta M times C square, and it is equal to 2.8 times 10 to the power minus 12 joules. And let's convert this into electron volts. One kilo electron volt is 1000 electron volts, and mega is 10 to the power 6 electron volts. And the conversion of electron volt and the joule is very straightforward. We divide with 1.6 into 10 to the power minus 19 joules per electron volt. Therefore, the Q value comes to be 17.56 million electron volts for this reaction. Now, this energy is given out to both of the particles, the helium-4 and the neutron. Helium-4 is a massive particle, and the neutron is a small mass particle, and it is these two masses that are sharing the Q value. One kg of deuterium and tritium mixture would allow a number of fusion reactions. Let us find out. Here it is 0.5 because of the 2 and plus 3 divided the average mass multiplied by 1.6 into 10 to the power minus 27. So the total number of fusion reactions would be this. This amount of reaction will generate about this much energy. And this is 4 gigawatt for 24 hours. You can convert this because gigawatt, watt stands for the joules per second, and giga stands for 10 to the power 9. And you can figure it out with the help of the time, given that this is equivalent. 1 electron volt is also used as a unit of the temperature. Temperature is always expressed in terms of the average energy, and the unit is electron volt. For example, the way to say is this kT divided by E in terms of the electron volt. So if you substitute temperature here, you will be getting the average energy. So instead of saying this is so many degrees of Kelvin or so many degrees of Celsius, we say this is temperature in so many electron volts. So substituting the temperature in Kelvin, we get the temperature in terms of the energy. So 1 electron volt is basically 11,000 Kelvin degrees. And 17.56 million electron volt is roughly 2 into 10 to the power 11 Kelvin. This is equivalent in temperature. The energy and the temperatures are interchangeably used. If we want to see how the energy is distributed in the reaction products, then energy released is in the form of kinetic energy. Kinetic energy is not equally distributed over the product because of the momentum, because of the masses, and we need to conserve the momentum. So let's see here, 0.5 multiplied by mass of the particle A times the velocity squared of the particle A, and similarly, so it is half mv square, which is the kinetic energy of the particle 1 and the particle 2 energy, and both are added together gives the total fusion energy. Similarly, the mass of the A, velocity of the A is the momentum of the A and must be equal to the momentum of B times the mass of the particle B and the velocity of the particle B as a momentum. And the directions are exactly opposite. If we use these two equations, we solve them simultaneously, we find the energy given to A is 0.5 times the mass of B times E fusion divided by the total mass of A and mass of B. So the energy part given to A is actually the fraction in terms of the mass of B. Similarly, the energy given to B is in terms of the fraction of mass A divided by the total. See the fraction? So E fusion is distributing its energy as a reciprocal mass. So we see here the two terms that the energy of A is related to the mass B and energy of B is related to mass A. And if we take the DT example, here we had the total energy released as 17.56. And this is helium nucleus, which is 4 times more heavier than the neutrons. Then it will be actually taking 3.5 million electron volt energy, and 14.1 million electron volt energy will be taken by the neutron. So very large energy, 14 million, will be taken by the neutron, which is small particle. So the fat particle will not carry large energy. The thin, lighter one will carry the more energy. So if we look at the key problems in the fusion, we come to know that the Coulomb barrier is one which needs to be crossed by the ions to get fused together. So this is the either it should be capable of having energy large enough to cross the barrier, or it should tunnel through the, it should have large energy or capability of tunneling through the high potential. So high kinetic energies are needed, and high kinetic energy means high temperatures are needed for the fusions to happen. Helium nucleus is lighter than the 4 protons, and the mass difference is this much, and the energy, which is 0.7% of the mass, disappears into this energy. 1 atomic mass unit is given by this, and so we can find out the difference in terms of the energy. And 1 mole of particles of the proton will give this large amount of energy, and you can convert this into the joules or kilojoules per mole. A typical chemical reaction gives 100 to 200 kilojoules, and nuclear fusion will give about 20 million times more energy per mole. It is equivalent to 150 million kilocalories per gram, compared to 16 million kilocalories per gram of uranium and 10 kilocalories per gram of gasoline. So you can compare and see That's roughly million times more, but correctly speaking, 200 million times more. 200 million times, 200 times 10 to the power 6 times more energetic, so more destructive. Fusion energy scope is very high as compared to the oil and gas, the chemical reactions. The selection of fusion process is a tricky process. If we have to choose, we have to look into the cross-section and the center of mass energy distribution. Here, 2, 5, 10, 20, 50, 100, and this is KeV, the kilo electron volt energy. So we have to choose a reaction which has a high probability of occurrence, and it must also require low temperature. Still, we need a temperature, but not that high. There are temperatures as high as 500 keV. Remember, keV equivalence with temperature. We see the tritium is unstable. It decays into helium-3 with a half-life of 12 years. So it does not occur naturally, and we have to make tritium. So DT reaction is a very good reaction, but T is required through other reactions. Free neutron produced in DT fusion reaction is potentially dangerous, so it can produce radioactive elements. This problem is with the DT. However, the DD reaction is low. It is not very competing at 50 to 100 keV. It is not capable, but DD is safe because it will be needing D only, not the tritium. Once we have produced tritium, then we can suggest this reaction. D helium-3 is more probable, but at high energies, so high temperatures, so it's not really that feasible initially. High energies are both the process of proton and boron 11 and helium-3. Helium-3 is also. So only choice is between DD and DT, and DD is more feasible because tritium is not needed here and it is unstable. You need to produce it. Fusion energy is really possible. We have seen center of the sun where the 16 million degrees are keeping the fusion going. In laboratory, high temperatures are needed to get the good rate of fusion, such as 100 million degrees. And one kind of fusion is this proton fusion. It's a difficult choice because of the high temperatures, very high temperatures. But other choices are the deuterium plus tritium, or deuterium, or DD reaction or DT reaction. So these will create the higher binding energy elements in the binding energy graph. So good reaction is D and D, and it leads to high energy releases in the fusion process. Natural hydrogen has the abundance of 0.0115% deuterium in it, which means the water in sea will have a reasonably good abundance. 1 out of 6,500 atoms of hydrogen in seawater is deuterium. So there are 1.0 times 10 to the power 22 deuterium atoms in 1 liter of seawater. 1 kilometer cube volume has the energy potential of 1,360 billion barrels of the crude oil. It's such a tremendous potential of energy that it cannot be ignored. Tritium is unstable. Its half-life is 12 years. So it's not naturally available. Tritium can be made by bombarding lithium-6 with neutrons. And extra neutrons in the T reaction can be used for this purpose if the reaction core is surrounded by the lithium blanket. If we surround the core with the blanket, then all the neutrons that are coming out of the core will hit the lithium-6 and will produce tritium, and that tritium can be recycled. However, tritium is radioactive. So, how one can confine the plasma, the ions and the electrons in a very high energy and very high temperature. Nature has provided a solution of using gravity and gravitational pull. It is such a tremendous force that the particles with this force can overcome the Coulombic repulsive barrier and then can fuse. Then there is a possibility of a magnetic confinement where the strong magnetic fields really allow the charged particles to get trapped and have the helical trajectories around it, and they are moving like spirals along the magnetic field lines. So stronger the magnetic field, the smaller will be the smaller will be the radius of such spirals, and will be a good confinement. So ions can be limited to a space, and electrons can be controlled, and you can keep them to avoid the striking of the wall, and you can also have the confinement. Then there is an inertial confinement in which the intense energy beam, such as lasers, are used to heat and compress the hydrogen so quickly that the fusion starts occurring before the atoms can fly apart. Before this sense, the sheer inertia helps them to get the compression. And the compression is so high that the density becomes very large as compared to the original density. About 1,000 times more dense they become. And once they become dense, then they can overcome the Coulomb repulsive barrier and can have diffusion. We stop here today's discussion, and we will continue our talk on the fusion reaction and how to control. But before we go further, we must study the plasma. What are really the things that affect the plasma, and how plasma important parameters in a reactor must be handled. So our next lecture will be about the fusion reactions and the physics of the fusion reactions. We stop here. Thank you so much.